Yes, I have a question, but in study questions set 8
Okay.
for number 5.
Number 5. All right. So I'm just gonna say this now. So the reason why that one doesn't have water is that it's not in the equation itself. Like if we were to add water to it, it would literally just, it would be there on both sides. It doesn't do anything to the equation itself, since they're both being combined, because hydrochloric acid is a type of acid and ammonia is a type of base. But the way that when acids and bases combines, they form a salt. And for them to form a salt, they need to combine completely. There's no oxygen in there, so they just completely combine. Does that make sense, Andrea? Other Andrea, sorry. Okay, cool. So for number 5, so what 2 variables are we using for number 5?
Pressure and temperature?
Pressure and temperature, right? So what equation are we going to use to solve this? Anybody have an idea? Is it Charles? Yeah, it'll be Guy-Lussac's law. So Guy-Lussac's, I don't expect you guys to remember the names, but if you can at least tell me, there we go. Nice, Stephanie. So it will be P1, I did a thing. So it will be P1 over T1 equals P2 over T2, right? We're doing problem number 5. Sorry, I should have circled it. So what are our givens? Like, what does it give us to start off with?
35 psi.
35 psi. And that's the pressure, right?
Yes.
Okay, and then for temperature?
Negative 10 degrees Celsius.
Okay, so when dealing with gas laws, do we have it in degrees Celsius, Kelvin, or Fahrenheit?
Kelvin.
In Kelvin, right? Okay, so what would it be in Kelvin?
So you add that negative 10 plus 273.15 Kelvin.
Okay, and that will give you
263.
263. Nice. Okay, and what's the final temperature that they give us?
40 degrees Celsius.
40 degrees Celsius, right? So what would it be in Kelvin then?
313.15.
Yeah.
313.15. So
does our pressure need to be in PSI?
it doesn't say that it has to be, but I mean, I think it's easier if they just leave it like that instead of having to remember another conversion.
So as long as we put the unit, we're fine, right? We don't have to convert it to ATM.
Yeah, unless it specifies what pressure, like if it says what will the pressure be in ATMs, then you got to change it. But if it doesn't specify, then I'd say just keep the pressure that it gives you.
Okay.
So what would your pressure be in this case?
I got 41.65.
Okay, there you go, 41.65.
But in his answers, he has 44 or 57.
44.
Yeah, that's true. It's a different one.
What question is this?
Number 5.
Question 5 for 8. Yeah, say 8.
The pressure be.
Okay. That's weird.
Oh, Got 41.65. And what did you say the answer to it was?
It was, well, he has 44 or 57.
If I remember correctly, this one you need to add either, I think you need to add the external pressure, but I think in this one you actually do need to convert from to atmospheres, but I wouldn't be too sure.
Okay, so we had
You guys
41.
remember to convert to Kelvin? The
Yeah,
temperatures?
we converted to Kelvin. Interesting.
Okay. Yeah, this was a problem we were dealing with about one.
So
We deal with this one at like every semester, I think.
if I add the external pressure, because it says it's going to be an apostle, right? Or something. It's, I think one of the PowerPoints, it gives you 13 PSI. So if you that add to 35, then in that case, it would give us 57.
So you add the external pressure to the initial pressure?
If I do that, then I get 57, but I wouldn't know what to do if I get this on the exam, you know?
Okay. So I guess with that logic, that still doesn't make sense. Okay. So basically, once you figure out what your initial pressure and temperature are, you'll add, I guess you'll add the external pressure to the initial pressure because that's what you're given. And when you add those together, that will help you in finding your external pressure. So you'll have 35 plus 13 over 263.15 equals whatever the final pressure is at 313.15 Kelvin. So this is your external pressure, if it's given. Take forever to write that.
Well, it's kind of weird, no? Because it's asking for the pressure on the tire, no? Like within.
Yeah, that's why I don't, like if there were leaks in it, then I guess I'd understand that, but there isn't.
Mhm.
What did he say your answer was again?
Oh, okay. So yeah, you can add, yeah. Okay. And then you put plus 13 over here. Because you guys said that it was either 44 or 57?
Yes.
Yeah, so we subtract 13 from 57, then we get 44.
Yeah, you'll get 44. I don't like that problem. But yeah, basically just add the external pressure to both.
All right, guess sounds good.
Because it's asking for the pressure on the tire. And so that pressure that's coming from the inside is also having that, it's affecting the tire, and then the pressure from the outside is also affecting the tire. So like, let's say this is the tire. So like, this is the inside of it. And so all this pressure is like pressing against it. And then the external pressure is also pressing against it. So that's why you'll add the 13 to both of it. Does that make sense to everybody? Yes, no, maybe so.
Yeah, now that you explain that in detail, now it makes a lot more sense.
Okay. Good. Okay. Yeah, if it should be multiple choice. He's not that much of a sadist. You guys should be fine. So, you guys have any other questions?
So we basically
Sorry,
add
complaints, panic.
Sorry?
We add the 13 to the initial pressure and to the final pressure?
Yes, because that external pressure is still acting on the tire.
Okay. Thank
Uh-huh. But make sure that you subtract the 13 after you do the whole multiplication, division, all that stuff. Oh,
Now you lost me.
okay. So like, you know how we did the whole, wait, that's it. You know how we did the whole P1 over T1 equals P2 over T2? And then it's basically P1, T2 over T1 to find P2? You guys all following?
Yeah.
Okay, so if there's an additional pressure being added to here, because P1, you already added the 13 too. So you multiply and divide, and when you get whatever number, then you subtract that from 13. So it'll be P1, T2 over T1 minus 13. Does that make sense?
Wait, could you do it with the numbers?
Yeah.
Okay. All right.
Sorry.
So got our P1, T1, our P2, T2. So we have 35 plus 13 over 263.15 equals P2 plus 13 over 313.15. So you add the 35 and the 13 first, which gives you 48 over 263.15. You multiply that by the 313.15. And that, but you still have this 13, so it'll be P2 plus 13. And so when you multiply that, you'll get about 57 equals P2 plus 13. And then you subtract the 13, and that's how you'll get 44 equals P2. Does that make sense? It's PEMDAS, if you guys remember that.
Okay.
Yeah,
So you just
that-
oh, so you
that-
just what the okay. I get it.
Basically, add what you can, subtract what you can, and then do what you normally do, and then you keep it going. I don't even know if that made more sense.
Yeah, dude.
Wait, so
Got it though.
All right, cool. So
are you guys recording this? Is this going to be on the
Yes,
YouTube
yeah.
channel?
it's
Okay,
going to be on the
cool,
YouTube
thank you.
channel.
Okay,
Yeah.
awesome. Thank you.
So someone said question set 7, number 4. Yay, I love this one. Okay, so for this one, it says that we're doing an oxidation from iron to ion. Yeah. What's the YouTube channel name?
I'll send the link.
There you go. So it goes from an iron 2 ion to an iron 3 ion, right? So when iron goes from a 2+ to a 3+, what's happening to it?
It's losing.
It's losing an electron, right?
Yeah.
So it just becomes plus an electron because the electron's removed from it. Now, we know that we're going from permanganate, whatever the oxidation number is for manganese, and we're going to a manganese 2 ion. So that's a 2+. So what would be what's the oxidation number for manganese and permanganate? Or better yet, what's the oxidation number for oxygen?
-2.
-2, right? Okay, so we know it's -2. So what's the oxidation number for manganese then?
Wouldn't that be?
I'm sorry?
7?
Positive or negative?
Positive.
Positive?
Positive, right? Because in order for it to equal the -1 charge that they have, it would need to be a +7. So it has an oxidation number of +7. So what does that +7 mean for manganese? Like since it has, I'm sorry?
What do you mean on that? What are you asking? That's interesting.
Yeah, basically, am I asking, is it losing or gaining electrons?
It's gaining electrons.
It's gaining electrons?
Losing.
Because it's becoming positive.
Yeah, it's
Yeah,
becoming positive, which means that it's losing electrons, right? So if it
No,
lost 7 electrons, what would be its charge? If it lost 7 electrons, what would be its charge then? Okay, we said that oxygen has a -2 oxidation number. So since it has a -2 oxidation number, what's the charge for oxygen?
-2.
-2.
-2, right? Okay, so
So positive
for,
5.
Wait. What's the oxidation number for manganese again?
+7.
+7. So if it has a +7 oxidation number, what's its charge?
+7.
+7. Beautiful. So it goes from a +7 charge to a +2 charge, right? So how many electrons would it need to gain to reach a +2 charge?
We need to gain 5, you know?
Gain 5, right? So +5 electrons. So from the first one, it goes from an iron 2+ to an iron 3+ with an electron removed. Is that balanced? Same amount of electrons on both sides? Yes, no, maybe so. Okay, why do you think it's not balanced? Aaron. Or does someone think that it's something else? Yeah, they need the same electrons. So iron 2+, when it becomes iron 3+, it loses an electron, right? So since it lost an electron, we added an electron right here. So is it balanced?
Yeah,
okay.
it is balanced.
So that one's balanced. What about down here with manganese? When it becomes a +7 to a +2, you guys said it gained 5 electrons. So is this one balanced too?
Then yeah, it should be.
Yeah.
Okay. So I guess the only question that I still have for you guys real quick, which one's being oxidized? This one or this one? The first or the second one?
Second.
The second one's being oxidized?
The first one.
No, yeah, the first one.
Okay. So why is the first one being oxidized?
Because
it's losing an electron.
It's losing electrons. Perfect. So as future reference for an oxidation half reaction, since you guys know it's losing electrons, the electrons will be on the right side. And since that one's oxidation, we know the other one should be reduction. So the electrons will be on the left side, right?
Yeah.
So we wrote the balanced equation for both of those. So we finished this one, and now it says to write a balanced ionic equation, right? So in order to do that, well, iron's getting rid of 1 electron, but magnesium needs 5. So what exactly do we need to do for that to work out for both of them? Nice, Moses.
Multiply by 5.
Wait. Did you say divide or multiply?
Multiply.
Okay, so we're multiplying what by 5? What are we multiplying by 5? Which half reaction?
The iron.
The iron, right? So it will. So for this next question, it will be 5, 5, 5. And is it balanced now? Is there a balanced number of electrons going from the iron to the magnesium now?
Yes.
And there's your answer. I knew someone was going to ask me to go over that question. So actually, wait, let me double check because I might just be going crazy. But I think it's enthalpy. Yes, it is. Okay, so did any, like, I'm not expecting everyone to have done this, but like, was there anyone that asked Dr. Alexander how he was going to do his enthalpy questions?
I don't think so.
Yes, he's gonna give it to us.
He's
Oh.
going to give you the enthalpies for it?
Yeah.
So the
Okay.
point of these questions, for example, question 1, what you guys want to do, if you're just given the equation, you guys can look up the standard enthalpy values from the textbook, or from like just looking up standard thermodynamic
I
data
got you,
table.
Kevin.
So
And Melissa.
so I
actually,
think it would. What's up, Jeremiah?
it's because they're going to be on lockdown browsers, so they won't actually be able to look these up. But since he's giving it to them.
I mean, yeah. In the test, you're definitely gonna be given the problems, but in these practice problems, you have to look them up.
Okay, so I won't be able to give you guys the exact number. However, I can tell you guys this, like, we can go over the steps for these types of questions.
Yeah.
All right. So, just starting off.
Wait, for this one, we have to look up the enthalpies of.
Yeah,
formation,
you would have to look up the enthalpies of formation.
Maybe you can.
I can explain this one if you want.
Go for it. I don't mind being quiet.
I mean, dude, you've been talking the whole, like 30 minutes.
Yeah, my bad.
Get some water, bro.
Sure. Let me just go ahead and draw. Okay. Let's share. Excuse that my screen is so messy.
Wait,
All right. Sure, go ahead.
So for the standard enthalpy, I know he's gonna give it to us like you said, but is it going to be like per question, or is he gonna provide like a sheet? Because like the periodic table doesn't open or doesn't stay open, so I don't. Will it be like that? Because then that's the issue.
I'm not entirely sure because I'm not an Alexander peer leader, so I don't know exactly how he does his tests. Do you guys know how, Jeremiah, Corina?
Yeah, he should do it per question. Like the necessary enthalpies that you need, he'll give you for that question.
Okay, thank you.
Okay, so for this problem, obviously we're going to be given our enthalpies of formation for our iron to oxygen, and then also for our aluminum oxide. And then do I have to worry about iron and aluminum in this case? Do these have enthalpies of formation?
No.
Why not?
Because they're not compounds, they're just
They're elemental, yes. Yeah, so we don't have to worry about these. That's the main reason. Can someone give me the enthalpies of formation for these two? Because I have the textbook, but it's not in a binder because it's still wrapped up from when I first took the course.
I have it in a PDF. So maybe let me see if I can share my screen. Just let me look up the thing so I can the study questions. It's number 10. It's not loading. Oh, it's not there. Okay. Where is it? There it is.
Hope everyone's having a good day today in quarantine.
It smells like carne asada outside my house. I'm trying to make you guys laugh.
But okay.
It's not flexing. I'm envious of my neighbors. Okay. Okay. All right, I got it. I'm not sure if I can share my screen.
I'll have to stop sharing for a minute.
Okay, give me 1 second. And we are ready. Let me show my screen.
Claudia, Andre, and Andrea,
Oh,
can you guys take a look at
you.
question 7, Melissa
Oh, can you make me a
and
host?
Kevin's? Oh,
You.
I thought you were co-host.
No, I just came. I came
Okay.
later, so that's
There
why.
you go. Okay.
All right. Okay.
I can do question 7 if you guys want.
Yeah, go ahead. And
So really
then
quickly.
we'll do
Just-
that one afterwards.
Just that my
From module
my
10?
tablet's being weird, so
No
hopefully
worries.
can
It's
help.
okay.
Okay. From this one, right? This question?
Yeah. It's question set 10. Question 1.
All right. Oh, we're going to do this one first?
Because we're looking for the standard enthalpy of formation.
Okay.
I just needed
so,
the numbers.
Oh, don't worry. Okay, so for aluminum, we can just look at our handy dandy textbook. So we can look right here. We have solid aluminum. So here we can see what our enthalpy is. So this one, this column here is going to be our enthalpy. So the enthalpy for aluminum is just 0, right? Okay, so this is 0. My tablet hates me today. All right, let's look at aluminum oxide since we're already here. So here we have aluminum oxide, and we have this value. So we have negative 1,669.8. All right. Now let's move on to iron. Let's use the. It's gonna take. May take me a little bit. Sorry. Oh, there you go. Okay. So we have for iron. What do we have for iron? Oh, the iron one is probably on the last page. There we go. So for iron, we have
0.
0. And for iron oxide, which one is it? Which iron oxide is it?
Negative 822.2.
Negative 822.2. Okay, so now we have our enthalpies. You're usually going to be given them. So now what do you guys need to do with this information? You already know the enthalpies for each of the elements. What do you need to do?
At the, what was it, like reactants minus or something like that?
Well, it's with the minus, you're on the right track, but it's not reactants first. What is it?
Products minus reactants.
Yeah, there you go.
Products minus reactants, right? So it'll be the sum of the enthalpies of the products minus the sum of the enthalpies of the reactants times what?
Moles?
Times the moles, right? Or their coefficient. So, all right, so we have, what are we putting on this side? Excuse me, the phone, my phone keeps disconnecting. My phone is my webcam, so it keeps disconnecting. Sorry. Okay, what are we going to put here? This is the delta H of the reaction. This is for the products, right? So what are we going to add here?
Just negative 1,669.8. Plus 0.
All right. Plus 0, right? I should get an actual webcam. 0 times 2 because we have 2 irons. But it's just 0, so no problem with that. What about the reactants?
0 plus negative 822.2.
122.2. Okay. So what is our enthalpy of reaction, guys?
I get negative 847.6.
Negative 87.
847.
847.66. Oh, was that right?
Yeah, just 0.6.
Okay.
Yeah.
All right, guys. Does everybody agree with this answer? Everybody got this one?
Yes.
Yes.
Yeah.
Okay.
I
So it wasn't that bad, right? It was just looking up the values for these. It's a bit of a pain. So you guys might have noticed I did take a little bit long to find the values, but you guys can Google these too. So you guys can Google these values. You don't need to look up in your textbook or a PDF like I did. You guys can just look at these. These are like constant values, I know, depending on which one it is. All right.
What page is it on the textbook?
This is Appendix 3 at the very end of the textbook. This is Appendix 3. It's called Standard Thermodynamic Data, or Thermodynamic Data at 1 atmosphere and 25 degrees Celsius, which is just standard enthalpy, standard conditions.
Okay.
So it's Appendix 3 in your Chang textbook. It might differ from if you have a different one by chance. Okay, so we're gonna move on to number 7, right?
Yeah, Claudia was going to cover that one.
Okay, so I'm gonna just scroll down and let Claudia do the.
Okay. I know you also had a question on 6, but Andrea will do that one. Let me just annotate on this thing. Okay, guys, so first off, wait, is it on the 10th set of study questions? Yes. Okay.
It was on the 6th, or no? I mean on the 9th.
I mean, ninth set of study questions. Yes. Thank you. Let me just share my screen. Oh, unless it's gonna what?
Wait.
Mm.
Okay.
Okay, sounds good. Let me just find it if it's here because I have them open and tell me if this is correct. Is it this one? Before I even start.
Yeah, it is.
Okay, so we're gonna do 7. Okay, good. Now that I found it. So when it's talking about combustion, what are we always gonna have for the reactants?
Water.
Yes, we're gonna have water. Exactly. Well, actually, no, that's not for the reactants. That's for, but you are gonna have water. So what is the? So you always have an alkane. In this case, this is your alkane, which is heptane. And then you always have what else? What else do you have? In order to make water, what are you gonna have to have when you combine hydrogen with what?
CO2.
Yeah, oxygen gas. Okay, cool. So then of course you're gonna get water. And what else are you gonna get? If you do, this is a, technically.
CO2.
Exactly, awesome. So for combustion reactions, just remember that you're always gonna have an alkane and you're always gonna have oxygen gas, and that will always yield carbon dioxide and water. Okay, now from here, you just kind of have to balance it out. So let's do that. So first things first, I'm gonna say that carbon, of course, that's not balanced. So what am I gonna put in front of the carbon to make it balanced?
7.
Exactly, awesome. Yeah, we're gonna put a 7. And then we see that hydrogen's also not balanced. So what am I gonna put in front of the hydrogen in order to make it balanced?
8.
Okay, and now we just have to figure out the oxygens, and if they're even, then you could easily put a number here, and if they're not, we're just gonna have to do something else. So how many oxygens do we have? So we have 14 here, and we have 8 here. So how many do we have? 22? Yeah.
Yes.
Cool. I need some voices, guys. Okay, so if we have 22 oxygens here and we have right here 2, what number am I going to put in front of it to make it balanced?
11.
Yes, exactly. 11. Okay, cool. And is it balanced now?
Yes.
Yes. Okay. And that's pretty much how you do this problem. And you only have 1 mole of that. Do you guys have any questions on this problem?
For the combustion, there's always going to be an oxygen, right? That's what you said?
Yes, an oxygen gas. Yes.
Okay, thank you.
You're welcome. Okay, any other questions? Or else I could give it to Andrea. Let me see the chat. 11. Oh,
Wait, actually, there's a little bit more to 7.
okay, go for it, Jeremiah.
No, I don't want to do it. I'm just saying that there's like a little bit more.
Go for it. No, it's because I just go for it because I'm looking at the chat. So, or we could just move on.
Like, could you scroll down a little bit then?
I can explain it if you want.
Yeah, please.
Okay, so a lot of you guys may have seen. Oh shoot, I need to share my screen actually.
Yeah, hold up. Let me just.
One moment. I actually need to
Stop my
download the
sharing.
documents.
There you go.
Sorry, I need to download the documents too. Okay.
Number 11.
Okay. So. Okay, that didn't do anything. Okay, there we go. All right, so right now we just did this equation where it's C7H16 plus O2 yields CO2 plus H2O. Now, the next equation, or the next portion, is calculate the standard enthalpy change, which is delta H, of combustion of 1 mole of heptane. So basically, we're making heptane. So C7H16. And we're making 1 mole of this. I'm not chat. Don't forget. I know I have to. Jeremiah, wait, which one? The first one or the second one?
No, the first one is the good one because you're combusting the heptane, so that's the reactant.
Oh, was it 11, 7, and I forgot the H2O.
8.
Thank you. Okay. And then here we're asked to compute the standard for the combustion of 1 mole of heptane. Wait a minute. We're not making heptane, right? We're just doing the enthalpy, right? Of the reaction? Okay, we're burning it. Never mind. Forget everything I just said. All right. So here, basically, we're finding the enthalpy of the reaction. Where do you guys think we find the enthalpies of formations of these compounds?
They're gonna be given to us.
They'd be given to you guys. Ideally, yes. Hopefully, yes. But you guys can also Google it. Which one do we know right off the bat already?
Oxygen.
Yep. Oxygen. Oxygen is always going to be 0 because it's elemental. First of all, what's going to be my equation going to look like? What am I subtracting?
Sum of the products minus the sum of the reactants.
Yes, my sum of the enthalpies of the products minus the sum of the enthalpy of the reactants. Okay, can someone tell me what the enthalpies of formation for CO2 and H2 are? That way I don't have to Google it.
For which one, sorry?
CO2, H2O, and then also heptane if you can.
Give me a second. Okay.
Okay, thank you, Adriana. So negative 393.5 kilojoules per mole for CO2, and then just H2O. H2, I believe, is negative 285.8 kilojoules per mole, and then just heptane. So can kill me that one.
I researched it up and it was negative 145.47.
Thank you.
No.
Okay, so we use those numbers. Of course, these numbers will be provided to you guys. So how am I going to set up my equation, first of all? So here are going to be my products, minus, and then over here I'll have my reactants. How do I set up my equation?
So you basically, since carbon dioxide has 7 moles, you multiply 7 times -3.
93.5.
Yeah.
Okay. So 7 times -3, 93.5 plus
-285.8.
Well, 8.
There you go. Yes, don't forget you have your 8.
Oh yeah, I thought it was a G. My bad.
Now you're good. 0.8. Okay, and then for my reactants.
That would be -145.47.
So
Yeah, so -145.47 kilojoules per mole, and then my
Plus
11
times.
Yes.
0. Yeah.
And this just goes back to 0. Okay. So, Jeremiah, I'm not sure it's that one. Even in our workbook, it says it's -285.8 to make 1 mole of oxygen. So after this, what do I do?
5,040.9.
Or which portion?
The product.
Okay, so you said it was 5,000.
-5,040. 0.8. 0.9.
0.9. Okay. Oh, 5,040. Oops, not 5,400.
Oh yeah.
Okay, and then plus 145.47. And then what do you guys get as your enthalpy for your reaction?
4,895.
So -4,895. And then what's my decimal?
0.43.
0.43. There you go. Kilojoules per mole. Ooh, you guys got it. Cool. Is there any questions?
Good.
Everyone's good? Okay. Andrea, did you want to cover question 6?
Yes. Since it's on the same, I guess, study question, do you want me to just use yours or do you want me to pull up my own?
Whichever works.
I'll just use yours because it's a
Okay.
little easier or a little faster, I guess.
Okay.
Okay. Hi guys, in case you don't know me, I'm Andrea. So for this equation, we have to write a chemical equation for the corresponding enthalpy of formation of sodium chloride. So what this means is that we have to find the reaction that makes sodium chloride. So really quick, can someone tell me what sodium chloride is? Like what's its formula?
NaCl.
NaCl, perfect. Okay, so we are looking for the equation that reacts it, right? So obviously we're making NaCl, so we have 2 products, right? Can someone tell me what they would be?
Sodium and chloride.
Good job. So we have sodium plus chloride. Now really quick, would this chloride be, or would the chlorine be by itself or no? Would it have a subscript with it? Think back to which ones are your diatomic molecules. So that means which ones bond to themselves.
It will have a 2.
It'll have a 2, right? Okay, perfect. So now we see our equation. And to get the chemical equation for enthalpy, we always want to have 1 mole of product only. I don't know if you guys remember that, but our goal is to only have 1 mole of product. So that means that with enthalpy reactions, we can actually, instead of balancing it with full numbers, we can balance it with fractions. So by looking at this equation, is this balanced or no?
No.
No, right? So what throws off our balance?
The
sodium on the reactant side. I mean, sorry, chlorine on the product side.
Yes, good job. So our chlorine throws us off, right? On this side, we have 1 chlorine, and on this side, we have 2. So what do you guys think we should multiply it by to get it to be balanced?
2.
2?
By 1/2?
By 1, yeah, good job. So the reason it wouldn't be 2 is because with an enthalpy, or with a reaction that we want to find the enthalpy for, our product, we always want there to be 1 mole of it. Just because it, when dealing with your enthalpies and everything, it'll be a little bit inaccurate, I think, if we have more than 1 mole of it. So our goal is to have 1 mole. So now with this, is it balanced or no?
Yes.
Yes, good job. So yeah, that would be pretty much it for this one. So you just have to make sure, oh, I'm so sorry about that. Where'd it go? Okay, so yeah, you just have to make sure that it's balanced completely, but you never have more than 1 mole of your product. Any questions?
No, it's kind of like not like related to this, but like how you got the 2 again for the chlorine? Chlorine.
Okay, so think about going back a lot of modules. We learned our 7 diatomic particles, right?
Yeah.
So chlorine is one of them, if you remember.
I think oxygen is another one, right?
Yes. Oh my God. Yeah, so we have 7 diatomic particles, and the reason that our chlorine is it has the 2 is because chlorine is also part of those diatomic particles, as long as it's in a gaseous state. Any other questions?
Nope.
No? Okay, cool. Okay, then I guess that's it from me.
Wait, I have a quick question. With the halogens, have a 2 as well?
The halogens?
Yeah. Like for like.
Do you mean if most halogens are diatomic?
Yeah.
So the best way to remember if something's diatomic or not, it's by remembering this little mnemonic device. I'm not sure if that's how you call it, but it's have no fear of ice cold beer. And basically each first letter of this of the sentence is a diatomic element. So we have hydrogen, we have nitrogen, have no fear, fluorine, yes, oxygen, we have iodine, we have chlorine, and then we have bromine.
Oh, okay.
Mm-hmm.
All right, thank you.
That's the way you can remember your diatomic elements. All right, who's going to do the next problem?
Someone asked for number 8 on this same set, I think. I already did it, so I can go over that one if you'd like.
Sure. Let me go ahead and stop sharing.
Someone wanted to take a screenshot of number 7.
Ah, sorry. All right, let me stream it real quick. Sorry, I didn't see the questions. Okay, there you go. Type in chat once you finished with your ordeal. All right, Andre, you can go ahead and share your screen.
Oh, I was gonna use yours. Okay, never mind. No, yeah.
Okay, if you want. Okay, let me just screen.
Yeah, thank you.
It just makes it easier.
Yes, it's on the same one. Okay, So should I be able to annotate? Yeah. Okay. So it's saying the chemical equation for the decomposition of hydrogen peroxide is as follows, and then they give it to you, and luckily it's already balanced, so you don't have to worry about that. And then they say determine the standard enthalpy change delta H for the decomposition of hydrogen peroxide per mole of hydrogen peroxide. Okay. So this one's pretty standard. It's pretty easy. You just remember your equation. So it's the heat of formation of the entire thing is equal to the heat of formation of your, so let me write it down. I don't know how I'm going to do it how they wrote it in your workbook, okay? So it's the delta H, is that so small? Okay, hold on, give me 1 second. Okay, so it's the delta H, ooh, what does that look so messy? Hold on, I'm sorry if you can hear my dogs barking. Okay. Reaction. Wow, that looks horrible. Okay, so it's equal to the heat of formation of the the products. The products, I'm just going to put a P minus the heat of formation of the reactants, right? So, like he said in your test, it should be given to you, but oh, and then sorry, the summation. So remember that summation, that little E one, it's just the addition of. So add up all your heat of formations of the products minus the addition of all the heat of formations in your reactants, okay? So remember that in your test, it should be given to you, for all of these, but they might not give you the one for oxygen. Does anybody know why? Because you're supposed to know it. And I think we should all know, right? That the heat of formation for any stable or the most common form of an element, which is a stable one, is usually 0, right?
Yeah.
Does everybody agree? Okay. So by looking at that, so that's what they might do in a problem. They might not give you the oxygen one because you're already supposed to know it. It's a known. So in this case, we have to look them up, right? So if we look them up, what do you guys see? If anybody has because I know if you're from my workshop, hopefully you have the PDF of the book. But you can look it up anyways right now. So can anybody tell me actually the heats of formation for peroxide and hydrogen peroxide and water? And remember, it's in liquid form, so also look that because when water's in gas form, it has a different heat of formation. Okay, just be sure of that. Okay, yeah, but does anybody have it? So for hydrogen peroxide, does anybody have it? Or water?
For water, it's negative 285.8.
0.8, right? And we also always multiply it times the moles, right? So how many moles of water are there?
2.
2, right? Yeah. Yeah, 2. So we put a little here. So we're looking at our products right now, right? This is why we're having them first. Yes, and then for the H2O2, that's correct. So we're gonna add it. So there's 1 mole of oxygen, but we know that it's 0. So I'm writing it out anyways, just so you guys can know. But yeah, so close this in your parentheses, and so it's 2 times negative 285.8 plus 1 times 0, which is 0. So you're gonna keep it the same, and then you subtract by so there's 2 moles of hydrogen peroxide, and someone already said it's negative 187.6. So let's do our, so if you're writing this down, because I know I'm taking up a lot of space and I don't have much. So if you're copying it down, I'm gonna count down maybe 10 seconds just so you can take a picture of this or write this down. But this is how your math should look like. And so if anybody's actually doing it in their calculator right now, can you let me know what you got? Okay, so I'm gonna erase this, okay? So hopefully everybody got it down already. And did anybody get an answer? Yes, no, maybe so.
I'm working on it.
What's up? Okay, negative 196.4. So, am I done? Or, because remember, always read your problem carefully. So, am I done? Or what else do you think I need to do? Because I know some of you have probably already seen the answer. Like the answer
Divided by 2.
Divided by 2, right? Can you tell me why though?
Because there's two, they want it per mole, and you have
Per
to.
mole, exactly. So this is why it's very important to always read the problem very, very carefully. So per mole, we're doing it in a ratio of 2. So every 2 moles. So that's why we have to divide it by 2, because it's asking per mole, 1 mole, okay? So we divide it by 2 and you get what? I got around 90, what is it, 98.2? I know he has 98.3, but I mean,
0.2.
yeah, it's 1 decimal off, I guess, but still close enough, right? Because yeah, he has 3, I think. So I don't know what math might have happened there, but this is how I got the answer. But does everybody see what we did though? And is anybody confused as to why we divided it by 2?
I'm good.
No, is everybody good? All right. So yeah, that should be your answer. And
Oh,
yeah.
sorry.
Oh, what's
Real
up?
quick, again, like I get it, but just to like clarify. So let's say, for example, it was a 3 or 4 or 5, you would divide it by that number.
What do you mean?
Like instead, like you know where the 2 is, like if there was in place, like let's say a 3, then you would divide it by 3, right? Since it's asking per mole. It's just like hypothetical, but
Yes. Oh, yes. Yeah. I'm sorry. Yeah. So you want? Yeah. I know what you mean now. Okay. So yeah, you're saying if there was a 3 right here.
yeah.
Yeah. It's per mole. Yeah, because you want to get it down to 1, right? So yeah, you're right. Yeah, you would divide it by 3 if you were having a problem like that, or yeah, if your equation had a 3 in it and you were being asked per mole of it, yeah, divide it by how many moles there are of it to get 1 mole. Okay. So yeah, you're right. Okay, does anybody have any other questions? Yeah, that was a good question. So, but yeah, you were right. So you would divide it, yeah, by whatever coefficient you have. Yes. All right. So that was me. I don't know what other question needs to be covered, but yeah. All right, how do I stop annotating?
So you can click on select, and you can just that'll stop annotating.
Oh, okay. Okay, thank you. Yeah.
I mean, if anything, I'm struggling with oxidations and reductions.
All right.
Do you guys have an example for oxidation and reduction?
We can look at the homework now, or
I have an example.
I think the question said 7. There are some.
Yeah.
Oh, okay.
I have to download it.
Oh no, I got it.
Okay, I think I'll let you cover that one then.
Okay, so let me just open it up. And let me share my screen really quick. Okay, so number 7. Okay, so here we have an example, which is consider the oxidation.
Corina, we did that one already.
Oh, you guys did that one.
Maybe like 3 or 2.
Oh, 3?
Or not
right.
4, yeah.
Oh yeah, 2. 2 is good. I like 2. I actually like to use this one in my workshop. I've actually used this in my workshop. Okay, so number 1 said, oh, what the heck happened? Okay, it closed. I don't know why. Let me open that up again. I don't know why that closed, but let me just add some extra space so that we can work on this. Oh no.
You're not sharing your screen.
No, yeah.
Okay.
I'm not sharing it yet. I know. Just adding some extra space for it. Okay, so it says, a reaction that we observed in lecture was the reaction of aqueous copper 2 sulfate with iron metal to produce copper metal and aqueous iron 2 sulfate. Write a balanced equation for this oxidation reduction reaction. All right, guys, so what's the first thing that we need to do?
Write the formulas, I guess.
Write the formula, right? The formula is the equation, right? So just tell me what's the equation? What's the formula?
It's F.
Okay, let me help you really quick with that. So remember, it's the reaction of aqueous copper 2 sulfate with iron metal. So what are our products? How would you write them in a chemical equation?
Would it be 2Cu?
2Cu, just Cu?
Or no, 2Cu and then SO4.
Yeah.
It should be.
I just get confused whether to put that copper for that copper 2 if I put it as a coefficient, or is it considered like a.
Isn't it Cu3 and then?
Okay, so we have copper 2, which is Cu. Then we have sulfate. What's sulfate? What's the formula for sulfate?
SO4.
SO4. What's the charge?
-2.
-2, right? So what happens when these two come together in a compound? What happens to the charges?
They cancel out.
They
cancel out. So what's the formula then?
Cu
SO4.
Right. So just Cu SO4. Okay. So this is aqueous, right? So what else? What does it react with? It's the reaction of aqueous copper 2 sulfate with what?
Iron sulfate.
Iron, right? So how do you write it? How do you write iron?
Fe.
Fe. In what state?
2 plus 2.
What state? Not what charge, what state? Solid, right? It's not. Okay. So this reacts to produce copper metal and aqueous iron 2 sulfate. So how do we write that?
So
Cu plus Fe to SO4.
Cu plus
Fe.
Fe.
Yeah, SO4. Okay.
Because remember, this is iron 2 sulfate, so you won't have any crossing in there. You just need to. It's 1-to-1. All right. Okay, now we have the balanced equation. This is. Oh, wait. Is it balanced though? Is it balanced, guys?
Yes.
All right, this is balanced. We have 1 iron, 1 iron. We have 1 copper, 1 copper, 1 sulfate, 1 sulfate. Right, cool. Okay, so what's the next thing that we need to do whenever we have a redox reaction? What's the next thing that we need to do?
We need to write the oxidation numbers.
Right, we need to write the oxidation numbers. So what is the oxidation state for oxygen?
-2.
-2. What's the oxidation state on copper?
+1. Oof. Isn't it +1? No.
Right, which copper are we dealing with here?
+2.
+2, right? Should be +2. All right. So what's the oxidation state for sulfur? You guys know how to calculate that? Okay.
It's 6,
Nope.
right?
Hey. Do you guys know why it's 6? Okay, so let's see if you guys. Oh, did you want to speak up?
I'm lost. I don't know how to find it.
Okay, so Remember, what's the charge? What's the charge on sulfate, guys?
-2, right?
-2. All right. So what you need to know about polyatomic ions is that the sum of the oxidation numbers in a polyatomic ion, so like for example sulfate, is equal to the charge of that polyatomic ion. So the sum of the oxidation states is going to be equal to -2. So all we need to do is just find how much is the oxidation state for sulfur, right? So we know that the oxidation state on oxygen is -2. But we also need to take into account the fact that we have 4 oxygens. So what are we supposed to do here?
Multiply that by 4.
Multiply by 4, right? So that added to whatever the oxidation state of sulfur is, we'll call it Rx. The X, because you know, like X as in algebra, not X as in the person who broke your heart. All right.
Said B
So-
negative or B 6, positive 6.
That would be positive 6, right? Just solving for that. Just solving for that, right? This is -8, -2. That should give you +6. Okay. So what about for iron? What's the oxidation state on iron?
0.
0, right? Because it's just standalone. It's by itself. Nobody sharing with nobody. What about copper?
0.
0, right? What about, all right, so let's look at FeSO4. What's the oxidation state on oxygen?
-2.
What's the oxidation state on iron?
+2.
What's the oxidation state on sulfur?
+6.
+6. I mean, you guys can solve for it too, but you guys will notice that there's not really a change with sulfur here. But we do notice a change with some other compounds, right? So which ones are changing their oxidation states?
Copper.
Copper, right? What's it changing from?
From +2 to 0.
Mm-hmm. So if it's going from +2 to 0, what does that mean? What's happening to it?
It's gaining
It's gaining 2 electrons.
Gaining electrons, which means it's getting oxidized or reduced?
Oxidized.
Reduced.
Oh, reduced, yeah.
Reduced, right? Remember, reduced, it means that you're reducing the oxidation state. So you're making it more negative. So the more negative it is, it's becoming reduced. It's becoming more negative, it's reduced. Right. What else is getting, what else is changing in this problem?
Iron is getting oxidized.
Yeah.
Okay, iron is getting oxidized from what to what?
0 to
0 to +2. Okay, so it's losing electrons.
So it's getting oxidized.
Mm-hmm. So it's oxidized, like you guys said. All right, you guys are quick. Okay.
Don't forget this.
All right, what else? So we already found out which substance is being oxidized, which one is being reduced. This is what we have over here. Okay, now which substance is the oxidizing agent and which one is the reducing agent?
Iron is the oxidizing agent.
Iron is the oxidizing agent. Are you sure?
Oh, other way around.
Mm-hmm. So the way you guys can see it is that the oxidizing agent, hold on, let me just, so the oxidizing agent is what causes the oxidation to happen. So it's causing the other one to get oxidized. Causes oxidation. So if it's causing oxidation rather than going through oxidation, which one is the oxidizing reagent? The one that gets oxidized or the one that gets reduced?
Reduced.
Reduced, right? And in this case, just like Leslie is saying, thank you for answering, by the way. So Cu is the oxidizing agent because it's causing the iron to get reduced. So then conversely, what would be the reducing agent?
Iron.
Iron, right? Because it's causing the other one, copper, to get reduced.
Mm-hmm.
So it might seem a little bit counterintuitive, but if you guys see agent, that means it's causing that to happen. Like it's causing the oxidation to happen. It's causing the reduction to happen. All right. Does that make sense?
Yeah.
Okay. All right. So next one. Write an equation for the oxidation half reaction. Okay. So for the oxidation half reaction, what would be the half reaction for this one?
Half reaction.
So we actually did write something similar to what the half reaction would look, kind of like the incomplete half reaction.
It's just like missing
where is it?
it's, well, for the oxidation half reaction, would it be like Fe? I'm not sure exactly how to say it, but would you just add to the right side like plus E2 or something like that?
Right, exactly. Man, Sebastian, you're on fire. All right, so let's go ahead and write it then. How would you write it, Sebastian?
This is Moises speaking, but
oh, Moises, sorry. It's just that I saw that glowing.
It's okay.
I saw that glowing. Sorry, I saw
Like my
Sebastian
jokes,
glowing.
right?
It's okay.
My bad. It's hard to see. It's hard to see you guys when you don't open up your cameras because sometimes
Okay.
sometimes Zoom might confuse me. All right, Moises. So how would you write it? Sorry.
So Fe, and then the arrow. I'm not sure the exact wording. With
Yields. You could say
yields. Okay, and then iron plus.
And then
Plus E. Would it be like minus E or minus E2, or would it just be like plus E2?
Would be plus
Minus
E, 2E. I usually write it
2?
as 2E negative.
Because I kind of like while I was doing like separate videos on YouTube, just watching them, and they mentioned something that you can't ever write like minus on the right side when you're writing half reactions. Like you have to always use like a plus sign.
Yeah, you always have to do that because it's like a chemical reaction. So what you do instead is that you would write this E with the negative sign. And this indicates that it's an electron. Okay.
Okay.
Yeah, so that's I mean that's what I usually do. I don't know if anybody does it differently, but yeah, I would usually write it like this.
Okay.
Okay. So conversely, what would be the equation? Anybody want to help Moises with this? What's the equation for the reduction half reaction?
So isn't it like copper plus 2?
Copper plus 2.
Then, yeah, then copper 0. I think.
Copper 0, right? Okay. So in these half reactions, you usually add something that I didn't mention, but is really important, is that we basically add these electrons here so that we're able to kind of balance the charges. We're going to add electrons to the side that has like a positive charge. So for example, this Fe plus 2, where you would add these 2 electrons to add it. And Leslie, in the chat, she just gave me the answer. Thank you so much. Man, you make me proud. That's my student right there. She's on fire today. I'm proud. All right. 2E plus 2E on the left side so that we can have the 2 electrons. It balances out the charges on both sides. So we have 0 here. We have 2 electrons, which are negative. So this is 2 negative charges plus 2 positive charges. That's 0 overall for both sides. All right. All right. Good job, guys. All right. So are we done here?
Nope.
Okay, I have a question.
Yes. What's up?
Can you please explain how come on the reduction half reaction for D, how come you put the electrons like on the left side compared to the oxidation half reaction that they're on the right side?
Okay, so so this
Is it
is
that thing I
basically
said about like the minus and plus thing, or?
kind of, yeah. So what you want to do is you see you have this zero here, right? This this oxidation state, or you could also kind of think of it as a charge. You have a positive, you want the overall sum of the oxidation states to be the same, or the charges, if you want to see it that way. So you want equal charges or equal oxidation states on both sides. So you would add the electrons to the side that is more positive. Does that make sense? So right here you see you have iron +2. So that's more positive, right? So
yes.
Yeah, so to make the charges or the oxidation states equal on both sides, you would want to add the 2 electrons, which also signifies that these 2 electrons were lost from the reactant, right?
Yes.
So you started out with iron, and it lost 2 electrons, so now it's oxidized to iron +2. And conversely, you're going from copper +2, you add 2 electrons, which were transferred from the oxidation, from iron, as a matter of fact. So these are being transferred to copper, because it's becoming reduced. So it's going from copper +2 to copper 0. Does that make sense?
You're like essentially balancing out the electrons, like you're kind of balancing out the electrons. So, okay, I get it.
Right. So what you want to make sure is that you have the same amount of electrons on both sides, because you can only transfer that amount of electrons, right? So from the iron, you're transferring these 2 electrons to the copper, right? So you always want to try to make sure that it's the same. And that's also why you need to balance this equation, so you can make sure that you have the right amount of electrons being transferred. Okay. All right, are we going to deal with ionic equations in this exam? I have something in the chat. Chess, okay. All right, let's go for the next one then. What's the ionic equation for the overall reaction? So do you guys remember your ionic equations? How you would do total ionic and net ionic?
Like just like copper +2, sulfur +6, and oxygen -2. All right.
Yep, you would just break them up into their ions, right? So copper +2, sulfate plus iron, solid.
We have to determine their state, right?
Huh?
We have to determine their state as well, right?
Yeah. Oh, okay. So I need to, can somebody take over? Because I need, because I don't have my charger for my laptop here and it's dying. So
I got you, unless someone else wants to. No? Okay. Cool.
Hey.
All right.
Hey, Jer,
so
I'll be right back.
gotcha. Is this hers? It's going to die? No? Okay. So actually, so it will typically probably give it to you. Like here, it says that it's aqueous copper sulfate. That's why we have aqueous. And then it says iron metal. Metals are solid. And then aqueous iron sulfate. Aqueous solid. So that's how you'll determine if it's aqueous or not. So I don't like this color. Let me change
it. I think like the question is like we have to write them out.
Oh yeah. So this is like in the aqueous chemistry topic that that's like the earliest that you need to go back to. And so yeah, for ionic equations, it's important to put the state. That's probably the only reason why he put it here, because you wouldn't need it for a redox reaction. You need it for ionic equation. So that one's aqueous, this one's aqueous, solid, solid. I guess I'll just continue this real quick. So it's copper and iron, 2+, aqueous, and then sulfate.
So it's mostly gonna be given if it's aqueous and solid, right?
Yeah, that's pretty much like the only thing we deal with here. Like everything's aqueous. If it's not, it's a solid. And if it's anything else we don't understand, like I think that's a pretty good way to sum this up. Oh, you might see gases, but it'll say, you know, aqueous, that kind of stuff. I mean, she was already done with it. So like, do you guys have any questions about this one?
Just take a picture.
Go for it. Oh yeah, for the ionic equation, it's going to be the net ionic. That's why we have all of it.
Good.
Cool. So anyone else?
So we don't have to like find we don't have to find the aqueous and solid stuff, right? It's just
No,
like,
you don't.
Okay, cool.
It will be given to you.
So this reminds me of the how you call it, like they have a reaction and stuff like that. And
All right, sounds good. So any other questions? Anything that you guys are not so sure about? You want to get better clarification? Question 9, set 9.
Yeah, I was like in the chat. Someone put question 9.
Bet. Okay. So I'm gonna share it because she's not here right now.
No, I'm back. I'll go for it.
Well, that happened.
Don't worry. Go for it. I think this was 7, so you can open.
So,
you can open 7.
Yay! I love these so much. Okay, so assume question 9, set 9. This is set 9, question 9. Okay. So the reaction of sulfuric acid with sodium carbonate in aqueous solution is represented by the following equation. Assume the reaction is carried out under standard conditions. Compute the amount of pressure, volume, work there is done to the system. So what's this question asking for? Oh, thank you. So what's this question asking for?
The pressure.
It says, okay, wait. It says compute the amount of pressure, volume, work, right? So basically, what are we looking for? Work done by the system. Anybody have a guess?
Is that going to be like PSI or something? PSI? Is that what it means by pressure volume?
Well, it has pressure volume in it, but it says pressure volume work. So that means that you need the pressure and volume to get the work. I don't know why he put all 3 of those words right next to each other. Because that's pretty, it's interesting.
Is it the W minus P delta V?
Beautiful.
Are we going to be
yes.
At least.
Yeah. So we'll be using this equation, I'm assuming. So it says it's under standard thermodynamic conditions, and it's asking for 1 mole under 1 mole of sulfuric acid and 1 mole of sodium carbonate, right? So does anyone remember what the standard thermodynamic conditions are? It should be in module 8 for you guys.
It should be on 7 actually.
But this is work, so I think it should be in.
Oh, it's work? Okay.
I think.
I don't think it is.
I'm just saying I think. Like, I don't know. I'm here learning with you guys, like while we go over this stuff, low key.
I think STP conditions are, but I don't think standard thermodynamics. I think that was in lecture.
That sounds like something that would be the
Oh,
case.
standard thermodynamic?
Yeah, that's the whole
Okay.
reason why it's
Oh,
like,
so that should be 1 atm and 25 degrees Celsius.
Yeah.
that's for STP.
No,
First,
that's standard thermodynamic. STP is 0 Kelvin and no, sorry.
Gotcha.
273 Kelvin or 0 Celsius.
All right.
In this
So
equation, no, but in this equation, we're using the 25 degrees Celsius. I worked this out in the morning.
okay, so 25 degrees Celsius, right?
So you have to convert to Kelvin, but okay, I'm gonna stop now.
Wait. Okay. Wait. You just
Do you want me to explain it?
go for it because I'm confused now.
Okay, guys. So I think he went over this in lecture. I don't really attend his lectures, so I can't really tell. So what you're supposed, since it's talking about standard thermodynamic conditions, and we were talking about these, it even said it in that table where it gives you the enthalpies of the other ones. So when it comes to that, you have 1 atm, and then you have also, 25 degrees Celsius, but that converted to Kelvin, what is that, guys? I think 290 something, I don't remember.
298.
Awesome, yes, 298. Oops, I put 8 for some reason. 298.15 Kelvin. So we already know, and then we're using only 1 mole of each one, right? So we already know something else. So I'm just gonna put N equals 1. So what is the only thing we're missing from this equation, the work equation, that we don't have given in the problem?
We have to convert the ATM. Don't we convert the ATM to joules or something like that?
Actually, yeah, at the end, yes, because work at the same time, it gives you liters times ATM, right? So yeah, you are gonna have to convert that at the end to joules. But what are we missing in this equation? Because it only gives you standard thermodynamic conditions, which gives you the pressure. It gives you Kelvin, which we don't technically need in that equation, and it gives you 1 mole. So what other equation do we need to use in order to find the missing element from this work?
The ideal?
Yeah, the ideal gas law, exactly, which is PV equals nRT. And the reason we're using this one, can someone explain, or can Camila explain why we're using the ideal gas law?
Because we're missing the volume.
Yes, we're missing delta V, exactly, guys. So this is what we're trying to find, and then after that, pretty much easy peasy, lemon squeezy, except when you have to convert, right? So we're just gonna plug all of these. Again, it's standard thermodynamic conditions. So it's gonna be 1, because it's 1 atm. So you don't have to put that there, but just so you guys can kind of visualize it. And then we're only using 1 mole, right? 1 mole of sulfuric acid reacts with 1 mole of sodium carbonate. So it'd be 1. And then what's our constant in the ideal gas law? Exactly, 0.0821. Awesome. And then our Kelvin, which is everything, which is 298.15. And pretty much you just have to multiply all these together, and that will give you your volume. So what do you get, guys? Someone tell me, please. And this will give you your delta V, by the way. So what do you guys get?
244.78.
244.78. Is that what everyone gets?
Isn't it 2.4? No, 24.4, sorry.
I got 24.47 or
I got
48.
24.47, 49.
24.47. Yeah, that should be the
478, yeah.
Yeah, Yeah, it is standard conditions, but it would be standard thermodynamic conditions. So yeah, you're right, Alan. So this is your delta V, and now all you have to do is plug it into this equation. So for work, how many ATMs do we have in standard thermodynamic conditions? What's the pressure?
1.
Sorry, I worded that very, very incorrectly. And what's our delta V?
24.478.
Exactly. Cool. So technically, this is the same thing. So W.
I could put negative.
Yeah, it'd be the negative. Yeah, don't forget your negative because that changes it by a lot. So then it'll just be negative 24.478 liters times ATM. But again, work isn't measured liters times ATM. It's measured in what?
Joules.
Yeah, exactly. It's measured in joules. Sorry, I'm erasing things constantly. It's just I don't have space. Okay, and in order to convert to joules, what do I have to multiply or divide by?
101 point.
Do I multiply or divide it?
Multiply.
Yeah, you multiply by 101.325 because that's joules. Because in 1 liter times ATM, there is 101.325 joules. And once you get that, I think Dr. Alexander's study questions, it gave you 2.5 something, negative 2.5 times 10 to the third, right? That should be your answer. I don't know why he didn't round here and why he rounded there. So if someone knows, tell me. But that would be your work in joules. But since it's talking about, what is it? Compute the amount of pressure, volume work that is done. Okay, I actually don't know why, but he converts this to kilojoules. If someone knows why, is it because it's, I don't remember, I explained it. He converts this to kilojoules, and that's like your final answer, or maybe joules or kilojoules. So how am I going to convert negative 2.5 times 10 to the third joules to kilojoules?
Is it multiplied by 1,000?
Would it be multiply or would it be divide?
Divide.
Yeah, it would be divide. So because again, there's 1,000 joules in 1 kilojoule, right? So when you do that, you should get, what should you guys get?
We get 2.5 kilojoules.
Exactly, kilojoules. And that's what the study questions say. Do you guys have any questions on how I got these answers?
Just so you guys know, the reason why it's in kilojoules, it's because it's greater than 1,000. And usually if the amount of joules you have is greater than 1,000, he would rather be put in kilojoules because like there's less zeros. So just take that into consideration.
There you go. There you go. I didn't really know why, and I didn't want to say something wrong. So yeah, there you go. Any questions on how I got these answers?
Or when we're dealing with the work formula, we do it on Celsius, right?
For work problem, well, we don't.
Because I know that for one of them, we stay with Kelvin, and the other one, we just stay the same.
Oh, okay, I get what you're saying. Okay, so for work, if it doesn't give you delta V or P, it just depends. You are gonna have to use the ideal gas law, and that one you do have to always convert to this one, Kelvin. Well, this is your constant. This one to moles, this one to ATM, and this one to liters. But for calorimetry, is I'm pretty sure what you're talking about.
Yeah, the ones that you stay with grams, liters, and Celsius.
M set. Yeah, this one you could stay in degrees Celsius. This one is in grams. And then your Q is in joules, and then your specific heat is in joules, grams times degrees Celsius.
Also, yeah, I got it confused. Yeah.
No, don't worry about it. Just remember, if you use your ideal gas law or your gas laws, any gas law, you're just gonna have to convert everything to either Kelvin, moles, what else? ATM and liters. Okay, I'm just gonna clear everything. Does anyone have any questions? No. Oh, I already cleared it all. Or Jeremiah did. Okay. I'm just going to take your guys' silence as a no. So that's it.
Does anybody have any other questions that, or yeah, any problems that they want us to still go over?
Okay.
Yes, no, maybe so.
You could type it in chat. Is everyone tired? Yes. It says
You're
wait.
good.
Oh,
You're
Camila's
good,
like,
Camila.
wait. Okay, we'll wait for you, Camila. Don't worry.
I'm not gonna lie, guys. This exam's scary, but you guys are gonna be good for this because you know things now. You know more things than we do. Well, you know, that Dr. Alexander is giving you. Also, I hope you guys have been going to lecture because he's been
He's
a lot
sad.
of things. Huh?
Will this be recorded and posted? Huh?
Yeah.
Yes, it will.
No, we haven't gone over everything. That's why we're just like, we're hitting what you guys want first, and then like, if there's time or something, I guess we can go over something else. As long as you guys give us like a topic or something, we can go with that too.
Can you go over electron configuration?
Got you. Okay, so like the topic as a whole or one of these questions?
The topic as a whole.
All right. So do one of you guys want to tackle it? Or do you want me to? I'm pretty confident in module 11, so it's up to y'all.
Yeah, you go for it, Jeremiah.
All right. So for electron configuration, there are a few things that we need to keep in mind. First, let me pull up a lovely periodic table. Oh, just FYI, Claudia, that wasn't to everyone. That is not it.
Thank you. Let me do that again.
Wait, give me a second. Periodic tables. I know I have one. Maybe it's downloads. This is why you guys should organize your stuff.
Just search it up in the top right side.
You are so right. Periodic table. Perfect. Okay, so a periodic table. You guys see these things all the time, right? So for electron configuration, if you guys have looked at them before, there are a few things that we need to take into consideration for periodic tables. The first thing are the rows, right? So when you guys see the numbers on for electron configuration, they go based off the row or the energy level, however you want to call it. So let's say we're talking about hydrogen. What energy level is it located?
You
We
mean
will
as
do that
S?
right now, Paula. Huh?
You mean like
One?
S? Okay.
Yeah, it will be in the first row. So it's in the 1 energy level. If we were to look at sulfur.
So that means 1N, right?
Wait, what? Could you repeat that?
Like, because you know how there's columns, what, like 1, 2, 3, 4, 5? That's when you take it as N1, right? If I remember.
Yeah. Oh, yeah. That's for quantum numbers. But yeah, we'll go over that after this. Like, I can go over it together. But yeah. So first things first. Like, the rows are the energy levels. So for sulfur, what energy level is sulfur in?
3.
3, right? So now we know each of those. So 1, 2, 3, 4, etc. So so now we've done energy levels. The next thing that we need to know are the subshells. So each area has its own subshell. This area is S. I probably should have chosen a different color. Let me know if you guys like have a problem with it. This one's P. This one's D. And then this one down here is F. So for quantum numbers, since like it goes basically hand in hand, if you see it over in the s orbital, L will equal 0. If it's in the p orbital, L will equal 1. If it's in the d orbital, L will equal 2. And then the f orbital, L equals 3. So let's say we're looking at chlorine. What orbital or what subshell is it in?
P.
P, right? So L would equal 1 for quantum numbers. So when you guys see the 1s, 2s, that all has to do with the amount of subshells that they go through. So when you're doing electron configuration, you're going from every single row element and counting every single one of those. So like if we were looking at oxygen, we know that it passes the first row and that it's in the S. So 1s, and there's 2 in that row. So it would be 1s2 because we have 2 electrons in that one. Then we go to the second one. So it's 2s2 because there's only 2 rows in the s orbital, or 2 columns in the s orbital, sorry. And then in the p column, we have 6.
2p4.
Yeah, 2p4 because no, you're right because we have 1, 2, 3, and we stop at oxygen on 4, so it would be 2p4. So we basically are counting all the electrons until we finally reach whatever element we're going for. Does that make sense? Anyone confused?
What if you need to go to iron?
Okay.
Like if you need to continue to iron.
All right. So I'm sorry
if that's going to take forever. I don't know.
No, you're fine. Okay, I'm going to erase this that way. Is everyone clear on this? Anyone need to take a picture? No, right?
I don't think that we'll get it anyways. No offense.
That hurts.
You look back at it, I don't think they're gonna get it like that.
You know what? You might be right. I mean, we'll go like more in depth in your respective like workshops later. It's just like, I guess, to touch base real quick. So which one? You know what? Instead of iron, let's do chromium. Because, you know, we love chromium. So chromium, it's in a d orbital, right?
Yes.
We can all get behind that. Okay. So how many energy levels does it go down?
4.
What energy level? The fourth one, right? So that means we can automatically, okay, well, 1s2 because that's the most you can have, 2s2, 2p6 because there's 1, 2, 3, 4, 5, 6 rows in the p, 3s2, 3p6, and then 4s. So for the d orbitals, there's a special rule that whatever energy level that the element's on, you subtract 1 from it for the d. Which sounds weird, but as long as you understand. So like this d or this row that's on d, it's on the 4th row, but we'll put it as 3d. I'm sorry?
But it's actually on 3rd, yeah.
Yeah. So it'll actually be on the 3rd row. So chromium. So the lovely special thing about the d orbital is that, so we have, let me use a different color actually, that way it's easier to see. So we have 1, 2, 3, 4, 5 orbitals for the d subshell, right?
Yes.
So what these transition metals want to do is they want to have these as full as possible. So they either want to have 1 in each one, or they want to have it completely full. So if there are 5 orbitals in the d subshell, yeah, I'll do chromium 2+ right now. So if we have 5 orbitals in the d subshell, what's the most amount of electrons we can have here?
10.
10, right? Okay, and if they were all unpaired, what's the most that we could have?
Oh, what?
If there's only 1 in each one of these orbitals, what would be the most we can have?
10.
No, if there's 1 electron in each one. So like, let's say we get rid of...
Oh, 5.
5, right? So chromium, it has 4 in its D shell right here, right?
Yeah.
So it's 1, 2, 3, 4. But it still has this one that's empty. So since the 4s is above it, it can pull one of those electrons down to make it so that the d orbital has 1 in each of its orbitals. So it will end up being 4s1 and 3d5.
But this is like when I got this from Claudia too, and it was on Dr. Alexander too. But we I believe that Dr. Alexander wants to
putting me on the spot.
I know.
Well, basically, you told me like, well, you told not just me, but we're supposed to drop the D and like get the S on top of it because it's supposed to be more charged, I guess. That's I think what I'm getting from Dr. Alexander.
He said that, no, it's because what I told him is to switch the 3D with the 4S because technically the 4 is a higher energy level than the 3.
Oh, yeah.
You know how Dr. Alexander doesn't like it when you put 4S1 and then 3D5? And I'm
No,
like...
okay. Yeah, you can put it that way. The only reason I put the 3D in front of the 4S was just so that you guys could see
Visualize.
that I'm pulling one of these S's, one of the electrons from the S to the D first.
Yeah.
But yeah, basically put it per energy level. I'm not.
Yeah, because he was saying that in lecture, I believe, today too.
Okay. Yeah. So. Okay, everyone understands how we got this, right? Any questions on this?
So you pretty much put 3 because it's like the level before the 4th energy level, and then you just drag an electron from the previous level to that one. Is that what's going on here?
Yeah, that's why there's 5 electrons for the D.
Yeah, it's because for chromium, I can't annotate. Yeah, there you go. For chromium, and also the other one would be these guys here, right, Jeremiah? Correct me if I'm wrong.
You're right.
I don't know if it's just for chromium, for copper, right? Yeah. So for these, either they want to be half full or they want to be completely full.
You can also do it for vanadium and nickel. Just so
yeah. So.
Do you need to remember them? I don't know.
I don't know. I think the only ones you need to remember is chromium and copper. Okay, that's it.
Wait, nickel counts too?
Okay. Well, if you guys want to know more about these exceptions,
you just threw me off.
No.
Don't worry about nickel. Don't worry about nickel. Don't worry about nickel.
If you want to know more about this, stay later. But otherwise, don't worry about it. So for the chromium 2+, you're literally just taking electrons away. So the first place you're going to take an electron away is going to, you guessed it, from the highest electron or energy level. So since the highest is the 4th, we're going to take an electron away from the 4th. Okay, we need to take away another electron. So we're going to take an electron away from the d orbital first, which will be 4. So it will be 1s2, 2s2, 2p6, 3s2, 3p6, and then 3d4. Make sense? Any questions?
So basically, you just take an electron from the highest level.
Yeah.
Okay. Thank you.
Yep. And okay, wait. Before we go more into depth with this, there was someone that wanted to go over something.
One of the
calorimetry. Okay. Yeah. So one more calorimetry problem, super quick. So I don't know. Does someone have an example? Maybe 8 calorimetry. No. You guys all know how to do number 1? I think that's like the only one that we didn't go over. All right, cool. Well, we'll just go over.
Yeah, I was actually down to ask about that one. So yeah.
For number 1? All right, cool. So it says, how much heat does it take to raise the temperature of 36 grams, 25 degrees to 47 degrees, right? And then it gives us all this like extra given stuff, which is necessary, but it's given. So heat, that's Q, right? So what What formula are we going to use in this case? Based off of what they gave us. Anyone have any idea?
Q equals ms delta T, I think.
Beautiful. Yeah, because we have a M, we have our S. Oh, SPHT, that stands for specific heat, in case you guys didn't know. And it says in joules per grams Kelvin. It doesn't, well, yeah, so we'll just go with that. So what's our M? I just said it.
36.
What's our M? 36, right? What's our S?
I have a question.
0.40.
0.40, right? Okay, and so it says in Kelvin, right? So 25 degrees Celsius, what would that be in Kelvin?
298.15.
298.15, right? Oh.
Yes,
so isn't specific heat usually joules per gram times degrees Celsius? Is that why we're where we're converting it to joules
Kelvin.
Or to Kelvin? Sorry.
Yeah, we're only converting it to Kelvin because of what the specific heat, whatever the units are for specific heat, that's what we need to make sure we have for everything. So since it's in grams, this needs to be in grams. Since it's Kelvin, these need to be in Kelvin.
Also, there's times when you actually have to convert them.
Yeah, so just look at whatever units you have for your specific heat and you're good.
If we're looking for specific heat, do we go for Celsius?
Yeah, go for Celsius if you're looking for specific heat.
Wait, Jeremiah, I have a question.
What's up?
For the degree Celsius, can you convert those to Kelvin?
Yes.
Oh, okay,
so
cool.
okay, I learned this yesterday in my okay, we will go over a gas law. So I learned yesterday that so for when there's a change in temperature, since degrees Celsius and Kelvin, you add to them, no matter what you change it to, you're still gonna get the same number. But to stop you from being confused, make sure to change it to whatever it's asking for. So it says Kelvin, so we changed this to Kelvin. So it's 298.15. And then for 47, what would that be?
320.
320?
Yeah.
Okay, and that gives you?
$22.
22, nice. So 22 times 0.4 times 36. What will that give you?
$316.8.
316.8. Beautiful. And that will be your joules. And that's it. For calorimetry, it's just plugging in.
Wow.
Yeah.
I like that.
Yeah, honestly, probably, hopefully, the easiest thing that you guys will need to do since it's plugging in compared to the others. Any questions on calorimetry, heat, work, this good stuff?
So the answer was 316.8.
Yeah. Yeah.
Okay.
Any other questions on that, or are we good? All right, I guess we're good. So gas laws. So for gas laws, did you mean like a PV equals nRT, or did you want something more along the different types of laws?
Yes, please.
The PV equals nRT? All right.
Well,
Is there anything about Avogadro's gas law?
I think Avogadro's is the one where it's at STP with the 22.4 liters equals a mole, I think.
Let me just make an announcement, Jeremiah. So the review session is technically over.